Okay. Hello, everyone. I'm Alvaro Lozano-Robledo, and this is a graduate course on elliptic curves, on the arithmetic of elliptic curves. I'm a professor at UConn in the UConn math department, and I'm going to be the instructor for the class. You can see on the screen my email address and my website. For the students that are registered in the class at UConn, I'll send you some details with the office hours times, which I have not yet decided. For people if you are following this class in spring 2021, there is, in addition, in the website for the class, there is information about how to join a Zulip channel in case you have questions or want to participate and interact with other students. There is that. Let me talk a little bit about the website for the class. So here is the website for the class is up here under my website. You can click on teaching and you can find the link to the website for the class. There is a lot of information on the website, a course description, some prerequisites for those students that are not at UConn or at UConn. So what I basically I'm going to be requiring is a year of abstract algebra. So that means a course on groups, rings, fields, and up to some understanding of Galois theory. Although whenever Galois theory comes up, I will also try to review a little bit of like what I actually need from Galois theory, which is not a lot. And recommended preparation, you would get a lot more out of this course if you've already seen a course on algebraic number theory and a course on algebraic geometry. For the algebraic geometry, I will start with a review of basic algebraic geometry, so the basics of varieties, the basics of curves, up to a statement of the Riemann-Roch theorem, and then we will get started with elliptic curves. As for algebraic number theory, you don't need a lot of algebraic number theory. Most of what we're going to do will be over the rational numbers, but it turns out that the method I'm going to use to prove the main theorem of the course, which is the Mordell-Weil theorem, basically you get the statement for number fields for as much work as for Q. There is a proof over Q that I don't think is very enlightening, but if you do it over number fields, you actually get a little bit more out of it. So I will do it over number fields, and I will explain what algebraic number theory I need for that along the way. Okay, so yes, the videos will be posted on YouTube. So there's a YouTube playlist where I will be posting all these videos. And let me talk a little bit about books. So about books, so here in the website you can find a lot of resources on what books. The book that I will be following, so the main reference is, I have it right here, is, oops, the effects, can't really see it there, The Arithmetic of Elliptic Curves by Joe Silverman. It's an amazing reference for this, but then there is other books that will be that I suggest also as well, and other papers, and including, for example, a paper about the history of how the theory of elliptic curves has been built. There will be exercises. There's already here one homework set that is available to you to try it out. Many of the problems that I will be suggesting are computational. So there are a few that are actually best done with a computer, and those it would be in your best interest if you start learning something like Magma or Sage Math. I've made videos myself in introductions of how to use LMFDB, so that's a database of function modular forms, but in particular a database of elliptic curves that we will be looking at some point. But there are also videos about how to use Magma, how to use Sage to, in particular about elliptic curves and in number theory that you might find useful. Okay, so here is the first homework set. Let me just open it up like this. This is a little bit too small probably. So you can see I've written some preliminary exercises that have to do with the introduction that I will do to elliptic curves in a moment. And then also suggested 4 problems from Silverman's book. So this is problem 1.3, so it's chapter 1, problem 3 from Silverman. There is a huge collection of really good problems on elliptic curves in Silverman's book. So my homework sets is just highlighting maybe 2 or 3 from each chapter. But of course, there is many other problems that you might want to look at in the book by Silverman. And then I've included other problems that I include myself, some additional problems that are also meant for you to practice with actual examples of elliptic curves. Okay, here's the information about the Zulip channel, so you can look in the website. And then I have a schedule, a tentative schedule, or more or less how the course is going to transpire. So I will talk a little bit more about that in a moment. So let me get back to my slides. And right, so again, the people who are here live, if you want to send any, if you have any questions, if you put it in the chat or something, then I can address those, or we can talk about it later. All right, so yeah, about books, I've already said there's a bunch of books that are great. So these books in particular, these are more, these 2 books are on the undergrad level. While the ones below and many other books, there's more books in the website that I recommend. And there are even more books that I have not put in the website at the grad level. But again, the book that I will be following is Silverman's book on elliptic curves. Right. So what is the goal of the course? What are we going to do? The goal of the course is to prove the Mordell-Weil theorem. So here is the theorem. So what we want to prove is the Mordell-Weil theorem. This is not quite the Mordell-Weil theorem. What I'm going to state is sort of like somewhere in between Mordell's theorem and Weil's theorem. Mordell proved this theorem over Q, and Weil proved this in a much more general setting for abelian varieties over number fields. So we're doing a little bit of in between. So first, let F be a number field. And let E over F be an elliptic curve. So the goal is to prove that the set of rational points, so the F rational points, so the points of the elliptic curve defined over F is a finitely generated abelian group. The part that says abelian group, so that part is actually due to Poincaré. But the part that says that the group of rational points is a finitely generated abelian group, over Q, that's what Mordell showed, and over a number field, for even an abelian variety being sort of like a generalization of an elliptic curve, that is what André Weil proved. What this says, if you use the structure theorem of finitely generated abelian groups, this tells you that the group of F rational points decomposes as a torsion subgroup and finitely many copies of the integers and then that many copies, that's what we call the rank. Okay, and what we're going to do in the course is try to, first of all, prove this theorem, and then try to understand how to compute these things. So how to compute the torsion subgroup of an elliptic curve and how to compute the rank. And we'll see that, well, there are many shortcomings in the theory. So we have a full understanding of how to compute torsion subgroups, but not how to compute the rank of an elliptic curve. There is some conjectural algorithm. If you saw, there's a previous talk that I gave in the What is a Seminar, and that introduction to elliptic curves discussed a little bit what we know and about how to compute the rank of an elliptic curve. There's a question in the chat whether I'm planning to talk about abelian varieties, and no, not in this course. So that would be a follow-up course to this, would be, for example, follow Hinder and Silverman's book on Diophantine geometry, where they talk about abelian varieties and then prove the Mordell-Weil theorem over abelian varieties. So if I talk about abelian varieties, it will be just in passing. Okay, so that's what we are planning to do. So let me sketch how we plan to do this. So here's the plan for the course, and again, in the website there is some more detailed schedule of how I'm going to do this. I'm going to try to break up the videos in little pieces as we go along. And by the way, the notes where I'm writing on right now, I will be posting also on the website, so you don't have to hurry up and take notes behind me. So first of all, we're going to, because I do not assume that you've seen a full course on algebraic geometry, we're going to review basics of algebraic geometry. So that includes talking about curves, varieties in general, and we're going to talk all the way up to stating the Riemann-Roch theorem. And then we're going to start talking about basics of elliptic curves. And what we are going to do is, well, we are going to talk about, first of all, Weierstrass models. So we're going to see that we can write every elliptic curve, for example, over Q, over fields of characteristic 0. We're going to be able to write them in simplified models of this sort. And that is, in fact, thanks to Riemann-Roch. So it will be a really cool application of Riemann-Roch to proving that there is such models for genus 1 smooth projective curve with at least one rational point. We're going to be able to put them in that form. Then I'm going to talk about the group law. So the fascinating thing about elliptic curves is that there is a group structure, and we're going to do that twice. We're going to construct it geometrically, and we're going to also construct it algebraically as a group of divisors, and then show that this is the same thing. Okay. In fact, algebraically or geometrically, to prove that the group law is associative is quite a pain. But if you show that this geometric construction and the algebraic construction in terms of divisors is the same thing, in terms of divisors, the associativity is trivial. So we'll do that to avoid having to prove associativity geometrically. Okay. And then we're going to be discussing a bunch of tools of elliptic curves, which are things like isogenies. We're going to discuss one of my favorite things, the Tate module on an elliptic curve, and then something really useful, the Weil pairing, which has, so the construction of the Weil pairing is also one of my favorite things. and the theory of elliptic curves. So we'll construct the Weil pairing and then prove a few of the properties of the Weil pairing that are really, really useful later on. Okay. Then what we're going to do is I'm going to jump a little bit around in the book. This chapter comes a little bit later in the book, but we're going to jump ourselves to talk about just a little bit about elliptic curves over the complex numbers. So I'm not going to do a full theory of elliptic curves over the complex numbers. Basically, I'm going to state the uniformization theorem. The uniformization theorem tells you that an elliptic curve, so the points on an elliptic curve over the complex numbers, are actually in an isomorphism to a flat torus. So there is some lattice such that when you mod out the complex numbers by the lattice, you get the points on the elliptic curve. And this is useful. Well, this is interesting. It gives you some, like the Riemann surface, the Riemann structure on the elliptic curve, that if you've seen elliptic curves as tori, that's where that comes from. So we'll just talk about how that comes about, but I'm not going to prove that for the interest of time. Then we're going to do, we're going to take a detour, and we're going to talk about something a little bit strange. The first time you see these things is quite strange. So these are formal groups, which is, they are sometimes called a group law without elements. So just a formal group law without elements, and then we'll find ways to construct groups using these formal groups. So we'll make groups eventually out of these formal groups, and those will become those will be very handy to talk about elliptic curves over local fields in particular. So after that, we're going to talk about elliptic curves over finite fields, which in particular we're going to talk about the Weil conjectures, some very famous set of conjectures, and then also over local fields, and that's where the formal groups will come in to allow us to talk about local fields, and so local fields being things like also elliptic curves over p-adic fields, for example. And then we are going to use these things to do a few things. So first of all, this is going to allow us to talk about what can we prove about points of finite order, so about the torsion of an elliptic curve. We're going to be able to talk about good and bad reduction of elliptic curves. And we're also going to be able to talk about ramification, so ramification in division fields. Division fields being the fields that you get when you join the coordinates of points of finite order on an elliptic curve. All right, so then we're going to be ready to start proving the Mordell-Weil theorem. So then we're going to be able to prove the Mordell-Weil theorem in two parts. What we're going to do is first, we're going to prove the weak Mordell-Weil theorem, so-called weak Mordell-Weil theorem. What it shows is that if I do, for example, EQ modulo NEQ, that this is finite. Okay, so whatever that group is, when you mod out mod n, you get a finite group, and then we're going to pair this with heights. So we're going to define a concept of heights of points on elliptic curves, such that when you put these two things together, when you have a group that satisfies the weak Mordell-Weil theorem that that modulo n, you get a finite group, and you have a theory of heights that has the properties one would want of heights, we'll get to that, that gives you the Mordell-Weil theorem, because we'll prove that 1 and 1 together gives you the proof of the Mordell-Weil theorem. All right, so once we have the Mordell-Weil theorem, and we know that, for example, over Q, that this is isomorphic to a finite group of points of finite order plus some infinite part, we're going to want to compute these things. And to compute, what is that? Compute some group of points, Mordell-Weil groups. Okay, this is going to be called a Mordell-Weil group. So how do we compute the Mordell-Weil groups? We're going to compute first the torsion. So the torsion will prove the Nagel-Lutz theorem, and then I will also show you how to use division polynomials to compute torsion subgroups. Then we're going to need to have some sort of theory to prove independence of points. So once we have points of infinite order, we're going to have a lot of points of infinite order, and we need some sort of base, a basis of points. But this is a module over Z. It's an abelian group, so it's not a vector space. So we actually need to know about Z independence. So how do we tell apart when points are Z independent? And what we're going to do is actually refine the theory of heights here to define canonical heights. And the canonical heights are actually going to give us a way to prove independence of rational points. Then we're going to do one more quick detour to talk about Galois cohomology. So we're going to define just H0 and H1 Galois cohomology groups, which we're going to put to good use to define Selmer and Shah groups, which are going to help us in building the theory of descent. So thanks to this, we're going to be able to do a descent algorithm in quotes, because it assumes that Shah is finite. But we have a method of descent, and in particular, we're going to build the descent via 2-isogeny or via isogeny to compute Mordell-Weil groups. And that's going to be the course. I think by then it will be the last week of classes, and we'll probably stop there. I'm not going to be able to talk, for example, about many things. I'm not going to be able to talk, I don't think, about like modular forms attached to elliptic curves. I'm not going to be able to talk about much about the L function attached to an elliptic curve. Many other topics that are probably that belong in a course on the advanced theory of elliptic curves, and that would be a follow-up course or a follow-up reading group. So that is a summary of the course. So I'm going to stop this video here, And then I'm going to, in the next video, I'm going to start talking about another introduction to elliptic curves, a little bit more advanced than the one I did in the seminar, in the What is a Seminar. All right, so we're going to stop this one video.